Okay. I'll just wait for a couple of minutes. Okay. Once again. Okay. So I was doing this last time. Uh, so I was doing this last time. So recall. So we are looking at kind of the following scenario. I'm not going to repeat it. So we have a quantum state, fixed quantum state rho, something generic but fixed. We have a POVM. I'm going to we have a POVM. It has so its operators are lambda x indexed by x for some reason. So these are positive semi-definite operators, and I have an outcome set x. Okay. So clearly summation lambda x, x belonging to x is identity. Okay. And so phi rho is a purification. Okay. So E lambda, I don't know whether I mentioned this. This is a map. Sorry, this is a map. This is a CPTP map. Yeah, this is a CPTP map that takes you from L of H. So I might interchangeably use H and HA. Okay, that's the particle space. So this takes you from H to HX. What is HX? HX is just I want to give a space for the outcome of this classical random variable. So Hx is just span of x. So all the outcomes of the classical register are distinguishable. That's really what I mean. And it's in that space. So if my classical random variable, if my classical register has a distribution px, then the state of the register is given by this. Okay, this lives in, this is a density operator in H. That's all really I'm saying. Okay, so E lambda takes you from the particle space to a particle plus classical register. So what does it do? So if I have a state, if I have a operator S, it takes it to root lambda x s root lambda x tensored with xx. The other way to look at this is the following. So root lambda x s root lambda x divided by trace lambda x s tensor xx scaled by trace lambda x. So this that is what s goes to. So when I apply d lambda, so what does it do? I mean, the Choi cross operators are essentially root lambda x tensor xx. These are your Choi cross operators. So you can check that this is a CPTP map. Okay, what am I looking at? So, so when I make the measurement, how does the entire system evolve? So I have the reference space remains as is. I'm applying the E map lambda, right, on a purification P rho. So, and what I will do, as I told you, the outcome of a POVM, the quantum state is not well defined because of the rotation issue. So you can take a POVM, you can take a general measurement and you apply a unit rate at the end, the outcome statistics will be the same. Okay, so what we do, I am going to trace out the particle space and keep the correlation with the reference space as is. So I'm going to do trace over A. Okay. So remember when I operate this map, I'm getting something in HR tensor hx, right? So now I will do I hx. Okay. So this is a composition map. So I operate the measurement, then I trace out the particle. So I'll end up with just the reference and the hx. The correlation between the particle and the reference space, I mean the classical register and the reference space is intact because I'm only tracing out this. Okay. So this is my original measurement. Okay. I want to do some simulated measurement, and I want, so I'm going to operate this on P rho, do something, some weird simulation, right? And I want this to be small. Okay, so that's the idea. I'll go in steps. So one, I have to. So if I describe the solution, if I go through the entire problem and solution, you will not understand what's happening. So I will give you some intuition. So I told you the previous day, and I mean the previous class, and I hope you kind of maybe thought through it. So all our intuitions are coming from the classical. I mean, well, my intuitions are coming from the classical, and there's a very strong connection. So we will do that connection, and then you will get a sense of what's happening. Otherwise, you won't get a sense of what's happening. So remember, I told you the problem of simulating a random variable at a distributed location. Without, okay, so let me explain. So suppose you have, so fix a distribution. Let's fix a distribution. Pxy on x cross y. Two sets x and y have a distribution Pxy. So you consider the first scenario where Alice is given x and Bob is given y, and nature is giving according to the distribution Pxy. Okay. So suppose, so what does it mean? It means the following, right? So today they wake up and they see, say, 100 million samples of this. So they see x1, y1, x2, y2, x3, Y3, and so on, right? And they see 100 million samples, and they will try to compute the empirical distribution of any possible sequence A, B in that X and Y. Okay, so they have essentially they say, okay, what is the what does this joint distribution look like, right? In other words, they say, okay, so let's see, I want so they compute this n of AB given X and Yn, right? And they look at this, and they will observe that this is similar to PXY, right? Oh no, okay. So maybe okay. So I should not do this. So let me go one more step. So today they kind of wake up and they see 1 million samples. Okay, so they see X 1 million and Y 1 million. Okay. Tomorrow they wake up and they're going to see. So this is day 1. Next day they wake up and they're going to see another 1 million samples. So X to 1 million and Y1 2 to Y to 1 million. Okay, so they see every day they see 1 million samples, and they see this for say 100 days. Yeah, I don't know, I mean a huge number of days. So this is why huge number of days. And then after a huge number of days, they sit together and they say, okay, what is the so suppose I take a particular sequence, A1 through AN and B1 through BN, and I ask, okay, how many days did I see the sequence? Okay, so this is the huge a set of all so many days, so many sequences. They see how many times do I see this? Okay, and they will observe that this will be close to how many ever days they see times product Pxy of AI comma Bi. Right? I mean, equal to 1 through n. Yeah. So this is what they observe. So it is appearing as though every letter, right, every sequence, it is this whole thing and this whole thing, they are appearing IID, right? So if I look at what happens, if I look at the first sample, I can't tell about the second sample, I can't tell about the third sample, and so on. Right? That's what they observe. Now, let us cut one thread off. Let us only give X to Bob. So Bob is as Alice. So Alice is only seeing X. Okay. What should she give to Bob? Okay. So some protocol. So based on XN that she sees, she's going to send something out. And this guy, does something with whatever he gets. So he sends out a message as a function of XN. This message of XN comes to Bob, and Bob is going to use that to pull out a YN. And they do this for a huge number of days. And what they want is that this XN and this YN looks identical to here. Okay. So in other words, it should look as though, I mean, if there is a third party, he's given, say, this transcript. Okay, he's given this transcript and he's given this realization. He's not able to tell. He's not able to tell between the two at all. I mean, it looks like absolutely the same. Okay. Now the question is, how much information should X communicate to, should Alice communicate to Bob to enable this kind of a protocol? See, this problem is different from the earlier problem. The earlier problem, that is, was communication. You had a message M and you wanted to recover that M perfectly. Now it's different. Bob doesn't need to pull out a particular yn. Bob only needs to pull out a yn that there is a good chance nature would have pulled out. Okay. So the question is, what do you do, right? So how do you, how much message should Alice send to Bob, and what is the protocol? This is the question of interest. You might wonder, okay, why I'm relating the two. It turns out these two problems are very closely related. I mean, they're exactly, one is a classical version of the quantum counterpart. So first, is this problem clear to you? To everyone? I will just wait for everyone to put a thumbs up. Otherwise, I'm not going to go ahead.
Hello, sir.
Yeah.
Actually, sir, in the initial time there was some network issues and I couldn't hear it properly. So, could you just recap, what?
Which part? Which part? The quantum part or the classical part?
No. This how you are defining this problem, this classical problem.
The classical problem. Okay, classical problem is, the problem is as follows. I haven't defined, mathematically I haven't stated the definition, but I want you to first get the intuition. So Alice is getting X. Okay. You have fixed a set X and a set Y. There is a distribution Pxy. Okay. So imagine scenario 1 where nature will pull out X1, Y1, X2, Y2, so on IID according to Pxy. You're gonna get some realization, right? Now, in the second scenario, what I do is I'm not going to ask nature to give this Y. Nature is going to give only X to Alice. Clearly, everybody knows Pxy, so Alice can generate the Y. Okay, so she sees an X, she can just go pull out a Y according to this distribution. And she can do that every time she sees. Every X she sees, she pulls out a Y. So clearly, if you look at how does these samples X and Y look, it's going to look similar to what nature would have given, because she's essentially mimicking nature. But now what I do, I don't want Alice to pull out the Y, but like as in before, I want Bob to pull out the Y. Okay. Clearly, if Alice communicates the X, Bob can do that. Or if Alice herself pulls out the Y and communicates that to Bob, then Bob can figure out Bob has the Y1 to Yn. So that will require either h of X or h of Y number of bits per sample in general. So what she can do is she can wait for a long time, and she can compress that and send it with so much bits, or she can pull out the Y and send it out with so much bits. The question is, for our problem at hand, does Alice need to communicate so much? Okay. Can we, in some sense, reduce the amount of communication that Alice has to give to Bob? Okay. So that is the question. So what are we looking at? We're looking at something like this. Alice gets x1 through xn. So Alice is observing x. So she is observing something in xn. Okay. She has to send out some message of the xn that to Bob. This is all, the protocol is decided. It's only that what xn she sees today is different, and what yn Bob should pull out is going to be based on that xn. Okay. Protocol is fixed and understood. So she sends out a message to xn. Message as a function of xn, she sends out something to Bob. Bob is going to use that, and he is going to pull out a yn. And eventually, this xn and yn that Bob and Alice have, conked up with, should look as though nature has given them according to the distribution Pxy. Is that clear?
Yeah, okay, sir, I understand. So our main aim is here to somehow create this M, right?
Yeah, somehow create a protocol. Yes, you're right. I mean, more formally, I'm only telling message M, but maybe something else has to come from outside also. I don't know. It's not clear. But a protocol based on the XN she sees so that he can pull out a YN.
Okay.
Okay. So now let's get the intuition.
Hello.
Yeah.
Hello.
Yeah.
Sorry, just one question about the equation you had before.
Yeah.
With the CPTP map, I had a question there.
Yeah.
The very first page, I think. Yeah, this map.
Yeah.
So E lambda acts on, should this be L of H tensor H because you are acting on a purification here? Like L of H tensor H?
No. See, that's why I have the IR here, right? So IR tensor E lambda operates on L of HR tensor HR tensor H.
Yes. So what is HR here? HR is
your reference space.
Oh, so HR is same as H.
Yeah, so this is like your rho. See, E lambda applies on rho and you get this. So E lambda is applying only on L of H. Now I need something to when you make the measurement on the H space, it's the identity on the reference space. So that's what this is. Phi rho is living inside the reference space. So phi rho is a purification. So this is a density operator living in HR tensor H. And IR tensor E lambda is operating on this space.
Okay. Yeah. Now it's
Okay.
yes.
Okay, cool. So let's get some intuition here. So let's actually solve this problem. And we will, solve this problem in the sense, get the intuition of what's happening. And then we will do something very similar to this problem, to the quantum problem. That's why I'm kind of doing this. Okay, so the idea is the following. Okay, so clearly the question is, should I send so much or can I do less? And I asked this question, in the previous class, and I asked you to kind of think with it and come up with something. So I will give the answer now. So the idea is the following. So let's see. So what do we need to simulate? We need to simulate nature pulling samples according to PXY. Right. This is our final goal. Now, so let's look at our typicality picture. Okay, so this is so all my balls are the typical balls. So this is my X ball. This is my PX typical set. So this is T delta N PX. Remember, there is a joint distribution. So this is my T delta N PY. There's a joint relationship. It's not that everything on the right and everything on the left is coming out. So this is my this thing. Okay. So so there are 2 power n h of y number of sequences on the right. So what is nature doing? So if nature pulls out a particular xn, right, there is a ball of size 2 power n h of y given x sequences. So many sequences are there, and nature is going to. So today, if it pulls out an xn, right, it is going to pull out a yn uniformly distributed in this small black ball. If after 1 million days, say let's say 100 days, the same xn comes out at Alice, then at that time nature would be pulling out again something from here uniformly at random, something from this small little black ball uniformly at random, right? So this somehow you should bring this into your modeling, right? Similarly, there is another x tilde n, a blue x tilde n, and there is a x tilde n related to that. This may intersect, may not intersect. I don't care, right? Similarly, there is another x hat n. Sorry, let me write this into red. I'm going to focus on this. So I have another x hat n. There is a ball with that. This is of size 2 power n h of y given x again. And when x hat n is pulled out, I don't know where my yn is, but it is definitely going to be uniformly distributed in this ball. So if there is a protocol, right, this kind of a randomness also should come into that protocol. Otherwise, that protocol is not faithful to the nature simulation, right? So how do we do that? So the question is now, how do we? So in some sense, you get a sense, you get some idea here that somehow only thing that you should tell Bob is which ball to pull out. From that ball, he will pick randomly. If he does so, then you're essentially simulating nature, right? So you really don't need to tell the yn sequence. You may also not need to tell the xn sequence because there are 2 power n h of x number of sequences on the left, right? You don't maybe need to tell even so much. You really need to tell Bob, okay, I mean, which small ball that he needs to pick from, and from that he can pick randomly. I don't care, and he doesn't need to tell that to Alice, right? Okay, let's do something interesting.
Sir,
Yeah.
The thing that you told that after sending, we just need to send this region. Now, Bob can pick. What do you mean by randomly? Is it mean like he can pick uniformly from that ball? Because this typical, it is a conditional typical set.
So
My
what do you know about this?
distribution is
What is
almost
so
uniform.
what do you know about this? Probability that yn equal to yn given xn equal to xn. Suppose yn belongs to the typical set given xn. So conditional typical set. What do you know about this?
It's uniform quantity. 2
It
to the
is
power
uniform
minus
inside that conditional typical set.
Yeah.
So it is you. So this is nature. This is, by the way, nature. What I'm doing is actually p y given x of yn given xn. That's really what I'm calculating. Right. So nature is picking uniformly from this ball. You have no clue what is going to come. Today it's going to be this. Nature herself doesn't know. Okay. You get it? Yeah.
So Bob can also pick up just uniformly from that region. That will
But he
simulate
needs
my.
to know. He needs to know which region.
Yeah, I mean, you are saying that just send Bob from which region he needs to pick. Then Bob can pick from that region uniformly, right?
How many bits you need to tell Bob to tell him which region? How many regions are there on the right?
Like
For each
xn.
Yeah, for each xn on the left, there is a region on the right. So there are 2 power n h of x regions on the right. There are 2 power n h of x regions on the right. It may be wasteful to tell all of that because they are overlapping. Right? So that approach is still not doing us any advantage. So you still have to send 2 power n h of x. Right?
Yeah.
The question is, can we do even better? And the answer is possibly, and I will kind of indicate that. Is this okay so far? Okay. Cool. Okay, next. So what do we do? So I'm going to look a little bit closely into these balls and tell you that there is something more magical that one can do. Okay, and I will kind of indicate that. So this is 2 power n h of y given x. I'm just bloating up the same t delta n y. Okay. The total size is 2 power n h of y. Okay. Suppose something like this happens. Okay, what I will do, I will take this red ball, all the sequences in this red ball. Okay. Okay. Before I do that, maybe I'll do the following. I'm going to take 2 power n I of x colon y minus some small eta number of balls, number of bins on the right. So I'm going to just take what is this? 2 power n h of y minus h of y given x minus eta number of balls, number of bins on the right. Just empty bins. Okay, just take so many empty bins. So 1, 2, and so on. So this is 2 power n, this number. What I'll do, I will take all the sequences in my typical set and I will just uniformly throw them on the in a bin. Okay, so what I do, so I take a sequence yn. I'm gonna pull out. I'm not gonna pull out. I'm just gonna list each sequence, each typical sequence. I'll take a sequence on the a typical sequence, and I will randomly choose a bin to it and put it in that bin. Okay, so today the bin could be 73. I'll just go and put it in 73 bin. I'll pull out another yn sequence, typical yn sequence. I'll pull out a bin index, maybe 36. I'll put 36. Okay. Without keeping any reference to this conditional typical set on the left, I'm not going to do anything. I'm just going to take one typical yn sequence, put it in some random bin. Take another yn sequence, put it in some random bin. Take another yn sequence, put it in some random bin. I'm going to do that, and the number of bins is going to be 2 power n times I of xy minus eta. Okay. Let's look at what happens to elements in one ball or one conditional typical ball, right? Each fellow has been picked and randomly put in so many bins, right? What is the probability that in every bin there is going to be, less than one sequence? Suppose, there is no sequence in any bin. What happens? That means there are multiple sequences in some other bin, right? Okay, so maybe let me explain this number. So just give me 1 second. So I have 2 power n h of y given x number of sequences, right? Pulled randomly and thrown into the bins. I claim that because the number of bins, so I have 2 power n h of y divided by 2 power n h of y given x plus eta. So the number of bins is the number of bins is slightly smaller than the ratio. So every bin is going to be having at least one typical sequence. It is very unlikely that each two guys are going to get together and fall in the same bin, because I'm tending n to infinity. What happens is that all these red sequences will kind of fall in different bins, okay, because the number of bins are kind of smaller. You will find at least one sequence in every bin, and every bin will have at least one red sequence. Similarly, if I take any conditional typical set, so let me take another conditional typical set. Let me take another blue ball. This will also have 2 power n h of y given x number of sequences. I claim each fellow would have fallen in a different bin with high probability. Okay. So what has happened? All these red sequences have fallen in different bins. Very highly likely, you pick any conditional typical ball, its sequences would have fallen in completely different bins. Suppose I can get such an arrangement where every bin has at least one sequence from every conditional typical set. I mean, kind of the number adds up, because each bin will have around so many sequences, because I'm partitioning. So 2 power n h of y are the total number of sequences. I am putting them in bin 2 power n h of y, h of y minus h of y given x minus eta number of bins. So every sequence will have, every ball will have at least so many sequences. So this is h of y given x plus eta. And since the number of typical sequences are of the same kind, every every sequence from a ball goes into different bins, and you will see a representative in each bin of every conditional typical set. So what you have done essentially is, so if there is a green ball, here, the green sequences are coming here. If there is a, let's say a purple ball, the purple ball sequences are coming here. You have done kind of something of this sort. Suppose, you can do this. Then it gives us a clue. What do you do? So this bins is shared between both Alice and Bob. Okay. Alice will observe an xn sequence. So she'll observe an xn sequence. And nature will give her a bin index. So she goes into that bin and she finds something that is jointly typical with that xn sequence. Remember, this xn sequence is either a purple sequence or a green sequence or a blue sequence or a red sequence. And in that ball, she will find one yn that is typical with that xn. Okay. So, suppose her sequence happened to be the blue sequence. So she will identify, okay, there is this blue. So, suppose nature picked this bin. She chose this blues. She recognizes, okay, there is a sequence that is jointly typical with my xn. She will give the index of that sequence within that bin to Bob. Okay, so I'll repeat the procedure. What has happened? You have partitioned your entire yn space into, so my columns are the bins. Okay, so there are 2 power n I of x colon y minus eta number of columns. Each column is a bin. And nature, there is some random thing that will give out a bin index. And Alice observes xn. What Alice will do, so there is this common random bit that is coming. It's completely independent. It will tell you which bin index to see. In that bin index, Alice will see for a sequence yn that is jointly typical with her xn sequence. She will send the index of that sequence within that bin out to Bob. Okay. This choice of the bin index is completely random. It is completely independent of xn, and that is given to Bob also. So what Bob will do, Bob has got the index of the yn sequence in that bin. He's got the bin index because that is something completely, random. You give that to Bob. Bob will figure out the yn and pull it out. Okay. Now see what happens if I fix my xn. Suppose I fix my xn, nature is going to uniformly pick from the bins. And Alice is going to uniformly pick from the conditional typical sequences in that bin, typical with the xn. So what she's essentially simulating is she's simulating uniform distribution for in that conditional typical set. Similarly, you see if she has pulled out, if she sees a red xn, she will pick something conditionally typical with the xn that she sees. And again, nature is picking uniformly at random the bin. And if you tell Bob which conditional typical sequence she saw in that bin, and Bob is also told the index number, and he pulls out that yn, this xn and this yn will look as though it is coming from, nature. Do you kind of get this approach? If you have any question, let me know. If you
So just one question.
Yeah.
So given xn, Alice can definitely find a yn which is jointly typical with as xn, because each of these jointly typical sets have gone into each of the bins. I mean, any bin has all these typical sets, one thing from that.
Yeah, exactly. See, yeah, exactly. So each bin has a representative from every conditional typical set. So I'll say that again. Each bin has a representative from every conditional typical set. Now, so this bin index is just randomly picked by some third party. So when this random index is given, Alice is going to go into that bin, and she will see her xn, and she will choose a yn that is jointly typical with her xn. Now, what has happened is that this red conditional typical set has been stripped into the different bins, and so in some sense, your randomly assigning bin indices to every sequence. What it has done is every conditional typical set has got spread into all of these bins. So you will end up kind of so the bin index is telling you where in the conditional typical set you should look at, and Bob gets to know exactly that sequence. Bob is also given that index, and so he will figure out what that sequence is. So in some sense, you've been able to do what you want, but with lesser number of bits. Do you see it?
Oh, so okay, both of them know the random bin which has been picked.
Yes, both of them
And
know the random bin that has been picked.
oh, so what does Alice send to Bob exactly?
Alice sends the index of the sequence in that bin that is jointly typical with the xn she sees.
Oh, okay. Okay.
So with the xn, yeah. So Bob has got the bin index, and then Bob has got the index within that bin index. And so he knows a yn, he pulls that out. And because the conditional typical set has been spread apart in the balls, what it essentially is simulating is that you are uniformly picking from the conditional typical set. Okay, so
sorry, just one question.
Yeah.
So like if xn is fixed,
Yeah.
Then let's say that's the red sequence, then that whole red ball is spread uniformly amongst all the bins.
Correct.
And because the bins are also picked uniformly, you're essentially picking wine from the red ball uniformly.
Correct. Exactly. So I should come up with a way to assign every conditional typical element to so in other words, every bin must have a representative from the conditional typical set. If I can ensure that, then in every bin index that that is randomly given to Alice will be able to look for a yn that is jointly typical with that xn, and the process can kind of continue. And exactly. So each conditional typical set has been spread apart into the bins, and there is one allocation that kind of can do it. That's the non-trivial part. The non-trivial part is there one allocation that can do it? And probabilistically, we will show that there is indeed one such allocation. So every conditional typical set gets shared among the bins, and no matter which conditional typical set you have to pick from, you will find a representative in every bin, and you just uniformly pick the bins. Does it make sense?
Yeah.
Okay, so so I will go ahead with the quantum problem. Okay, so remember what is the quantum problem? So I have IR tensor trace A tensor IY. This is my I'll explain what is the connection between this problem and that problem through this now. So IR tensor E lambda operated on zero, right? So okay, so what is this? This is yeah. So let me do this calculation. So I'm going to do over not I'll do it over rho and then I'll do it more generally. So let's say so remember what all is fixed. So fixed rho belongs to d of h and lambda y, these are given to us. Okay. So let rho have a spectral decomposition. So we'll start with the spectral decomposition. So A, E, A, E, A. Okay. So I will take my phi rho. So this is my purification. I'll take in a very simple purification. So what are we doing? We are doing the following. So IR tensor E lambda operated on so phi rho. I'll just write this down. So this is what it is. Well, I started with that's why I remember I just I named my POVM as lambda x and not lambda y. So that's why I thought I was writing x and I wrote y. Okay, so this is lambda x. Okay. So this is x hat root lambda x EA hat root lambda x. Okay. I'm going to do okay. I will do the transform trick, but I'll actually do it without. I mean, I'll kind of do it as follows. So A hat.
So you also need tensor X.
Yeah, thank you. X. So this is not. This is there is no x hat here. There is only x. Okay. I will now do the. I'll actually do the transform trick, but I'll actually do it explicitly. I'm not going to just use it. So I claim here. I'll tell you what I'm doing. So I need one more. So what am I doing? I am just inserting an identity here and inserting an identity here. Okay, that's all I'm doing. Why am I doing that? Because I'm going to try and move the scalar and this scalar. I'm going to try and move that scalar and this scalar out to the left. Okay. So once again, I'll explain. So this was what I was starting with. I'm going to insert an identity here and an identity here. Okay, so that's what this is. That's what this is. I created a scalar and I can now move the scalar. Okay, so this because I'll be tracing out. Remember, why am I doing this? Because the next operator here is a trace over A. So I'm going to create myself a simple thing to trace over A. Okay, so that's really what I'm doing. So, so I claim this is gamma A hat. First term is as is. Now I move the scalar out. So I'm going to have EB root lambda X EA dagger. I'm going to bring the other scalar here now. There will be actually one issue here. So yeah, so there's this issue, but we'll get over with the transpose. Give me 1 second. Let me, yeah. So I'm going to actually put it in here. Okay. So EA Okay, so let me explain this step. So what I've done, I'm going to erase these. So I will identify the parts and you will get it. So this is as is here. This is as is here. Okay. This is as is here. And this is as is here. Okay. The only thing that has happened is that no. The only thing that has happened is this whole thing has come here. And this whole thing has come right beside here. Okay, and so this is these. So between this and this, the two scalars have come. The two scalars have come here. Okay, that's essentially what has happened. Okay, why did I do all this? Because we are going to trace out this, and when I trace out this, I'll get something simpler. So I claim the following. So this is A, and I'll let you check this. So X B hat gamma A hat EA lambda X root lambda X transpose. You'll have to check this, that I can do this by inserting a transpose in the middle. So EB hat root lambda X transpose EA hat. So what I've done, I've transposed this whole thing. So got this EA to the left and the EB to the right. Got the EA hat to the right and EB hat to the left. Okay. Tensor EB hat tensor XX. Okay. Now I'm going to do a trace. So now I'll do a trace over A. So now I'm going to trace out this part. So now I'll write copy. So now I'll do an IR tensor trace A tensor IHX. Okay, so I'm leaving the classical register as is and I'm tracing out the particle. So what do you get? So let me copy and then just do a head bra, I will change it to a bracket. So you have this, okay, and I'm tracing out. So I'm going to get, no, sorry. I'm going to do this. EB hat EB. Okay. So what is this? And so the A, this becomes identity. This becomes identity. And you have to just check this is what you get. You are going to get okay, so check that this is what you get. You'll get root rho lambda X root rho tensor X. So the lambda x's and the lambda x's become identity. Root lambda x and root lambda x become identity. There's only one thing that you will get a transpose here. Okay. So essentially what we have got is IR tensor trace A tensor IX operated on IR tensor E lambda operated on phi rho So I'm going to go one step ahead and I will say that if I do rho tensor n here, I get row tensor n here. Okay, this can be checked, but what I'll do is I will also, okay, maybe I'll do this carefully because there is one more thing. So I'm now going to, so what we did is we operated lambda x on row, right? Now I'm going to operate lambda xn. What do I mean by this? So this is my POVM, and I operate on, I'll call row tensor n. So I'm essentially doing n measurements. I'm doing n multiple n identical measurements on n copies of the state. Okay, so I'll call this omega, and so you just follow the same sequence of steps to show the following. So IR. So now I'm going to call this big lambda. So IR trace A IXN, because now I have n registers coming out, operated on IR. Well, I need IR tensor n also. IR tensor n trace E big lambda, that is n measurements, operated on P omega. So this is row tensor n. So this is, I claim, just going through the same sequence of operations, you will show this is root row tensor n, which is root omega. I'm writing it as row tensor n just for, just so that you can recognize with it. Row tensor n lambda xn row tensor n xn belonging to xn. Okay. So if you want me to go over these steps once again, let me know. I can go over it once again carefully if you want. Okay, since nobody is asking, I'll continue. So this is your so what have I done? I'm looking at the following.
Sorry, just one thing.
Yeah.
So in the last line, it should be trace of A tensor n.
A tensor n, yeah, you're right. Yeah, A tensor n. Okay. So what have I done? So remember I told you that I need to simulate the measurement. So this is whatever is there on the left is this. Okay, so this is, I have this on the left minus something else. So I have computed what is the left hand side. This is the left hand side. Now I need to come up with the measurement simulation protocol. Okay, so this is what I will do. So if you look at this thing, right? So I'll kind of tell you what is going on here. So if you look at this, xn belonging to xn, I can think of it as the following: px of xn So what is px of xn? So maybe I will not write it. I thought this was simple. So trace lambda xn row tensor n trace lambda xn row tensor n. So the reason I'm writing it like this is that these are trace unity, okay, and you are just mixing so many of them. Okay, so this is kind of analogous to pxn of xn times py given xn of yn given xn. So you're mixing multiple density operators, and that's what is your post measurement quantum state. Okay, so this is your distribution pyn. Okay, so that gives you the idea as to, so remember, what is cloud, what is covering was, you had a density operator rho, you knew you could simulate it as follows. You knew you could simulate it as follows, but what you did is you simulated rho tensor n as 1 by 2 power n r, some other states, rho xn of m, right? M equal to 1 through capital M. I'm trying to give you that sense here. So the left-hand side is a mixture of quantum states. Okay, so it is a mixture of quantum states. So you can think of it as like this: Pxn of xn, some theta xn. Okay, so you can think of the left-hand side as rho tensor n. Okay, you want to get close to this. You want to get close to the left-hand side. You know that you can do it either this way, or you can mix a uniformly number of states. That's kind of the idea. That's where the covering lemma is going to come. So I'm going to now choose some number of them uniformly at random, and I'm going to simulate this. So again, I will explain this once again so that it's clear. Remember, what was the covering lemma? So I had rho tensor n on the left, and I would simulate that using this. This is how I would simulate. Now look at what I'm looking at in the quantum measurement compression. I'm looking at the following: Pxn of xn. So what is my Pxn? So Pxn of xn is like trace rho tensor n lambda xn. Okay, so that's what that is. Times what do I have? Root rho tensor n lambda xn root rho tensor n divided by trace. I should say Pxn of xn. Tensor xn xn. So let me explain. Okay. So this is like your rho tensor n. Okay, I should not use rho. Let's call this theta tensor n. Let's call this theta xn. So my theta is px of x theta x. Okay. This is like your theta tensor n. You want to get arbitrarily close to that. And really, you don't need to mix all this. You can mix a subsampling of that. That's exactly what we will do here. Okay, we'll mix a subsampling of that. That's how the covering lemma is actually coming. So now I'll come to my. So do you see the? How many of you are able to see the covering lemma here? I know it appears way, but I'll tell you, we will actually do exactly what we did here. We will pick these states uniformly at random, just like we picked here, and we will mix a number of them to show that you can get arbitrarily close to this. And then somehow we need to come up with a measurement compression strategy that will end up giving you that. Okay, so let me go ahead.
Just one question. Sorry.
Yeah.
What is how is theta sub x defined here?
Theta sub x is exactly what we did, right? Theta sub x is this. So root rho lambda x
Lambda
root rho tensor xx divided by trace rho lambda x.
That's why that thing is equal to theta tensor n.
Yeah, that's why this is equal to theta tensor n.
Okay.
And so this is your theta x. So now you can actually even tell me the rates. Literally, you can tell me the rates. That's your theta x. And if I do this, theta xn, you actually get theta tensor n. You actually get this, right? So you can actually tell the rates also from here. So we'll actually do that. But what we'll do is we'll come up with a measurement compression strategy. So what I will do is, the idea is you create, so one approach, so the original measurement, what is the original measurement? So original measurement is just lambda xn. This is your original measurement. Now what I'll do, I'll create a new measurement. I'll call it a simulated measurement. So what I do is the following. So build k equal to 2 power nc POVMs. So I'm going to create a bank of measurements. So I'll call this a bank of measurements. How many elements are there? How many measurements are there in this bank? There are 2 power nc number of measurements in this bank. Okay. So measurement k, I'll tell you what is measurement, one generic k in that. So one generic k in that, I will denote it as theta k. So theta k is a measurement. So there are theta 1, theta 2, theta 2 power nc. Each one is a measurement. That means for each one, I should give you operators that sum to identity. So I will start with theta k. What is theta k? Theta k consists of theta m comma k. Okay. So each one is a positive operator value measurement, such that when I sum over m, how many outcomes are there? So the number of indices, the number of possibilities for m are your number of outcomes. So there are 2 power nr outcomes. Okay. So I'll state this once again. So I'm creating a bank of 2 power nc measurements. So k1, the index of the measurement in the bank is k, and it goes all the way from 1 to 2 power nc. Okay. Suppose I take the measurement, kth measurement, I'll call it theta k, and it has 2 power nr operators. So theta mk. So this is a positive operator. It's operating on n particle space. So I have m running from 1 to 2 power nr. Okay. So if I fix a k and I sum over m, I'm going to get identity. Okay. What is theta mk? I haven't told you what each operator is. So what you do, you build a table. Remember, your outcome space is xn, right? That's your outcome space. The outcome of one measurement is x. The outcome space is xn. You build a table consisting of 2 power nc columns. Okay, so 1 to 2 power nc. 2 power nc columns. And 2 power nr rows. So how many rows are there? 2 power nr. Okay. So each column corresponds to a measurement in your bank. So let me write this down. Each column corresponds to a measurement in your bank. So suppose I consider one such column. There are 2 power nr rows, right? These 2 power nr rows are the different outcomes of that measurement. So the rows in a column correspond to outcomes of a particular measurement. So I'll be more explicit. So fix column K, rows 1 to 2 power nr of column K correspond to the 2 power nr outcomes of measurement theta K. Okay, so let me now, so I've just built this table. I haven't told you what the entries of this table are. The entries of this table, so pick any row and any column, the entry will be, so if I pick, let's say, mth row and the kth column, I have a square. There I will put in some entry inside xn. Okay, so some n letter output xn of m comma k. I'll call it xn of m comma k. So essentially this is a table whose all the entries are elements from xn, and the m comma k entry is denoted xn of m comma k. So entries of the table are elements from xn. Okay. What is theta mk? Theta mk, this is the mth operator in the kth measurement. So I told you it kind of corresponds to the entry in the mth row kth column, right? So what is this theta mk? Theta mk is root omega, recall, omega is row tensor n, lambda xn of m comma k. I'll explain every term here. Root omega divided by 2 power nr trace omega lambda xn of m comma k. So I'll explain each term. What is xn of m comma k? Xn of m comma k is a vector of it has n elements, right? So x of m comma k1, x of m comma k2, all the way until x of m comma kn, right? So what is lambda xn of m comma k? Well, this is just lambda x of m comma k1 tensor lambda x of m comma k2 all the way tensor until lambda x of m comma kn. Okay, remember this is an element inside xn, so which means that each element is sitting inside x. So I can talk about this. Okay, so this is a positive semi-definite operator on H tensor n. I'm going to multiply on the left by root omega, on the right by root omega. So I have something, right? So let I know this is very hard, but let's I'll first explain the object and then I'll explain the intuition behind that. So root omega lambda xn of m comma k root omega divided by 2 power nr trace omega lambda xn of m comma k. I have defined something to you. I want to, so I have a collection for all m comma k, for all, so fix a k, I have a collection for all m equal to 1 to 2 power nr. So remember what I told you, I want to make a POVM. So if I add all the operators corresponding to a column, I should get identity, right? I have defined something, but if I add all of them, so suppose this was theta mk, if I add all of them, what will I get? M equal to 1 to 2 power nr, theta mk will give me root omega, and then I can put the summation, I'll put the summation outside. So 1 by 2 power nr, summation m equal to 1 through capital 2 power nr, root omega, lambda xn of m comma k, root omega, divided by trace omega lambda xn of m comma k. This is what I get. This is not the identity. So what I'm going to do, I'm going to just call this sk, right? I've summed over m, so it doesn't depend on m anymore. I call it sk, and I'm going to put on the left sk power minus half and sk power plus minus half. So I wish I could define my theta mk like this, but I can't. So I'm going to put an sk power minus half and an sk power minus half on the left, on the right. So this gives me a POVM. So what is my POVM? So my POVM.
So isn't the definition of theta recursive then? Like you're using theta mk to define theta mk,
No.
or is like
No.
like sk is the summation of
Yeah.
theta mk, right?
I'll tell you. Theta mk. Yeah, see, theta is the summation, sk is the summation of. Oh, you're right. I shouldn't have. This is what sk is. So theta mk is sk power minus half root omega lambda xn of m comma k root omega sk power minus half divided by 2 power nr trace omega lambda xn of m comma k for all m equal to 1 to 2 power nr. Okay, where what is sk? sk is 1 by 2 power nr summation m equal to 1 through capital M, 1 through 2 power nr root omega lambda xn of m comma k root omega divided by trace omega lambda xn of m comma k. Okay, so this is what it is. There's only one thing. If you so if you add theta mk's, what do you get? So if you add theta mk's, what do you get?
Just SK.
You will, if you add, so I'll just write it down. So if you add theta mk's, you're going to add these over m. So
Total identity.
So
You should get identity, right?
Identity.
yeah, you will add here. So this m will go transfer inside because k doesn't depend on, sk doesn't depend on m. You've already added. So you're going to add this. So you're going to get sk here. You're going to get sk. So there's an sk power minus half sitting on the left and an sk power minus half sitting on the right. Well, this will be the projector on the sk space. It won't be the identity. If sk does not span the entire space, then when I define to the power minus half, I'm essentially defining the inverse only on the range space of sk, right? So you will get so when I add this, I can call this pk, projector on the range space of SK. That's not a problem. It's still lesser than identity. So I can put a -1, which is I minus PK. Okay, so this is my POVM, the kth element of my POVM. Okay, so I have essentially, so what does this mean? The moment I have a table, right? The moment I have a populated table, I have a bank of 2 power NR measurements. So the moment I have a table,
Sir, why won't it be identity?
see, the inverse of an operator is defined as only, so if I have an operator A, lambda A EA, then A belongs A equal to 1 to R. Okay, and suppose this lives inside H, where dimension of H is D, which is greater than R. In this case, A inverse is defined as.
Oh, you're just defining like the function inverse.
Yeah,
Not the.
yeah. You don't invert the zeros. That's essentially what's happening.
But like, so then it's not exactly the inverse, right? It's some other thing.
Yeah, it's correct, right? I mean, how is the inverse operation on field defined? The inverse operation on field is not defined for the zero element,
Zeros.
right? So,
Okay, fine. So you're just like inverting in the range of A.
yeah, you're inverting only on the range space. I mean, you can look at this definition in build. Yeah. So
Yeah.
so that's why A inverse A is the projection on A. It is not, so it's pi A. It's not well, it's not pi A. It's projection on the space of A. That's why you need an additional operator to fill it up. But anyway, essentially what we will show is that SK is full subsuming. So I mean, in high probability, so it's not going to matter. But just for completeness, you need to put this. Okay, I think I'll continue in the next class. I might need an additional one. So I was planning to finish this in the next class, but I might need one additional class because possibly I will need one more additional class. So if some of you found this class little hard to follow, let me know. I'll be happy to again kind of dig closer. I know this is not trivial. This is the last topic in the course, and I think it's a very good application of the covering lemma. So I'm doing that. So anyway, I'm out of time, and I will again teach on Thursday. But if need be, I'm happy to have a session tomorrow if some of you want it.